Say when. Right. Hello. And what I'm going to try and do is a series of looking at AQA chemistry topic by topic. And what I'm going to do is have a look at topic one and work my way through to the end of the book. So we're going to start by having a look at atomic structure and get an idea about what that is, what it does, and everything else. The information I'm going to follow is from one of these books, and we're just going to have a look at this sort of book and follow it through. Okay, so atomic structure is our first little thing to have a look at. And what we discover is that basically we've got atoms. Now, what is an atom? Well, a definition of this, it is the smallest indivisible substance. You can't break an atom down into anything smaller than it is. If you do, which we can do, we can smash atoms, we don't end up with an atom, we end up with bits of an atom. So it's the smallest indivisible substance that still has all the properties of an element. Well, that makes life awkward because now we need to know what an element is. So this is one type of atom. So simply, chemistry is all about elements, and elements are one type of atom. You can have one type, lithium, you can have another type, carbon, sulfur, oxygen. If we combine these elements together, we can either just mix them together, in which case we get a mixture, or proper chemistry, we can take two or more elements and chemically join them together. Now, what do I mean by that? Well, to help, I've got some of these things, which are known as snatoms. And I'm just going to put some of those down and collect some of the other ones together. So let's take an element, and this is a carbon atom, and this carbon atom I can react with perhaps some hydrogen. So here's some hydrogen, and I can join that together to make here a molecule of methane, which contains one carbon and 4 hydrogens. Go back to the slide. So we've got a compound which is 2 or more different elements chemically combined, but we can also talk about molecules. And if we look at the screen here, we can see that a molecule here, this is hydrogen, 2 hydrogen atoms joined together. We can also look at perhaps a different one. We can look at here oxygen. Oxygen consists of 2 atoms of oxygen, and these are chemically combined together. I'm going to have to put in some bonds to join these 2 together. So I've now got a molecule of oxygen. I've got a molecule of hydrogen. We could do the same with perhaps something like nitrogen. Here we have 2 nitrogen atoms. They're chemically combined. So let's put the bond in, and I can arrange these. I will get them right. And there we've got the triple bond of nitrogen, the double bond of oxygen, and a single bond here of something like hydrogen, or maybe chlorine, or if I felt like it, maybe something like bromine. So these are all different molecules, two atoms of the same. Right, let's move back to the slide and go on. So we've got our atom, we've got our element, compound, and molecule. So let's see what makes up one of these atoms. Well, they have this nucleus in the center, and a lot of stories about how this was actually discovered. But basically, the nucleus consists of protons and neutrons. When we smash an atom, we discover that all these bits are to be found there. And going round those in orbits, or proper word, shells, are electrons. Let's have a look at trying to draw one of these and see what we can do. Just moving my snatoms out the way. We've got then simply a nucleus. So this nucleus consists of protons and neutrons joined together. I'm going to label my dark ones here. These are going to be neutrons. And I've got there another one, the white ones, protons. And going round this at a considerable distance away, this is certainly not drawn to scale, we've got a couple of electrons here in the same layer. This is an atom of helium. It contains 2 neutrons. It contains 2 protons, and it's got 2 electrons. When we look at these things, we see that the number of neutrons varies, but the number of protons and the number of electrons in an atom is always the same. If we draw another atom, this time I'm going to draw an atom of lithium. Lithium contains 3 protons. It contains 4 neutrons, and they are almost certainly arranged much better than I've drawn them. And going around this will be 2 shells. In the first shell, we've got 1 electron, in the outside shell, 1 electron, in the inside shell, 2 electrons. This is the helium structure, and there we've got the structure of lithium. So we've got 3 electrons. This gives the rise to the chemical properties. We've got 3 protons. This tells us what the atom is. And we've got 4 neutrons, which together with the protons give us its atomic mass. So there's our basic structure of an atom. Let's have a look at this in more detail. So let's have a look at the next slide. And our next slide is more about this atomic structure. These protons and neutrons are in a very dense core at the center of the atom, and we call this the nucleus. Really very dense. All the mass of the atom is found in that little piece. Going round much further, we've got the electrons, which really don't really have much mass at all. If you have to try and make an estimate for that, it's about a 2,000th of the mass of the nucleus. So really very light, but they have opposite charge to the proton. If you want to look at this, try to look at it at scale. If you took a P and put this in the center of Wembley Stadium, then an electron is going to be a grain of sand or salt somewhere outside of Wembley Stadium. So there's a lot of space, and all the mass is contained inside the nucleus. These electrons are spread out and they orbit around this nucleus, but a lot of people seem to think of them as sort of solid particles going round, but maybe we have to think of these more as waves, making us, if you like, a sort of a cloud around this atom, this nucleus. Okay, so there's our idea of atomic structure, and it gives us some idea about how it works. Now, our next problem we come on to is that of doing chemical equations. And chemical equations tend to give students an awful lot of problems, but they're not really that difficult. And what I'm going to try and show you is a way of trying to do this easily. So let's have a look at the paper and we'll have a look and see how we can do this. Let's take a very simple chemical reaction. And if we take some acid, and I can think of one which is hydrochloric acid, HCl, and I'm going to add to this some sodium hydroxide, NaOH, sodium hydroxide. This is going to react together and we're going to form a salt, NaCl, and in this case it really is common salt, plus what we've got left is water. Well, that works quite nicely because I've got one sodium on this side and I've got one sodium on that side. I've got one chlorine on this side, one chlorine on that side. I've got one oxygen on this side, one there, and then we've got these two. And so everything balances. But not all equations are like this. Some are a lot different and cause a lot of problems. So let's just take a slightly different example and see what happens if we do this. So let's take a different acid and let's take nitric acid and let's add that to some magnesium. So the magnesium's going to react. We're going to form magnesium nitrate. And it's got a really peculiar way of trying to write the formula. Plus water. No, sorry, plus hydrogen. My fault. Now, let's see how this balances. Well, I've got one magnesium on this side, one on this side. We've got one nitrate group on this side, but oh dear, look, we've got two on here. So it's not going to work. It's not going to balance. So let's see if we can find a nice, easy way of trying to balance this equation. And what I'm going to ask you to do is remember something, that you can't be asked to do something. CBA. We can all remember that really quite nicely. So C stands for the chemical, B is the before, and the A is the after. So let's write down our chemicals. We've got hydrogen. Now this one, NO3, I could write it down as nitrogen and oxygen, but this NO3 here is going to end up over there, so it's not really going to change. So I'm going to make my life easy, and I'm just going to write down NO3, and I've got my magnesium. Let's have a look and see how many we've got before. I've got one hydrogen before, The nitrate group, I've got just one of those, and my magnesium, one of those. Afterwards, what have we got? Well, we've got two hydrogens. We have got NO3 twice, so we've got two of those, and we've still got one magnesium. So let's go through trying to balance, and to balance this, really quite easy. If we've got two at the end of the reaction, we must have had two at the beginning of the reaction. And this is where we put a big number 2. So I've got two NO3s. Well, if I've got two of those, I've also got two hydrogens. Well, look, 2 and 2, they're balanced. 2 and 2, they're balanced. And we've got 1 and 1, it's balanced. So this is now a balanced chemical reaction. Let's have a look and see if we can see a few more of these. And what I'm going to do is I'm going to try and load this up. So if we have a look at the screen, I'm just going to cheat for a minute, and I'm going to go and get myself some questions to sort of have a look at this. And as you've noticed, I'm well prepared, so I didn't bother to load it up. And what I'm going to do is have a look at balancing an equation. So let's just load up some questions to have a go at trying to balance. And let's make it a little bit bigger so you can see it. And we're going to start with an equation here. So I've got some Na3PO4. This is sodium phosphate, plus I've got some potassium hydroxide, KOH, and this is going to give me some sodium hydroxide plus some potassium, K3PO4, potassium phosphate. Let's have a look at that. So I've written out the equation, and I remember when we do this, I simply can't be asked to do this. CBA, the chemical before and after. And I really can't be asked to write that out again, so I'm not going to bother. So what have we got? We've got some sodium. The phosphate before, phosphate afterwards. I'm just going to write that down all in one go. Then we've got some potassium, symbol K, and OH. OH before, OH after. They're going together. I'm going to keep them like that. So let's now have a look at the before. I've got 3 sodiums before, and I've got 1 phosphate. I've got 1 potassium before and 1 hydroxide. And after, 1 sodium, 1 hydroxide, 3 potassiums, and just the PO4. Well, it's not balanced. Let's see where to start. Well, if I've got 3 sodiums at the beginning, I've got to have 3 at the end. And we're going to use a large 3 here. Let's change that. And if I've got 3 sodiums, then I've got to have 3 OHs. So we better change that one. If I've got 3 OHs at the end of the reaction, I had to have 3 OHs at the beginning of the reaction. And this means that the potassium, we've got to have 3 of those. Sodium balances, the phosphate balances, the potassium balances, and the hydroxide balances. So here we have our balanced chemical reaction. Let's have a look at another problem. The next one on this list is looking at magnesium fluoride. So let's have a look at magnesium fluoride, Mg F2. This is going to react with Li, lithium, and then going together, CO3 makes carbonate. And this is going to give me magnesium carbonate, MgCO3, plus some lithium fluoride. Now, if we look at this equation, we can see, and we'll switch to the piece of paper, that our magnesium reacts with 2 atoms of fluorine, making magnesium fluoride. Now, how this actually works out, we'll look at in another lesson. The lithium here is reacting with the carbonate, and the lithium, we've got to have 2 lithiums because lithium is only 1 plus and the CO3 is 2 minus. But when magnesium combines with this, magnesium is 2 plus and the carbonate is 2 minus. So that's balanced as a formula and lithium fluoride. Let's work out how to balance the equation. And so we start off with my CBA. I can't be asked to do this. I've got some magnesium. I've got some fluorine or fluoride. We've got some lithium, and I've got carbonate before, after, so I'm going to just put down CO3. Typically when I do this, I rarely make my lines long enough. Before, we've got 1 atom of magnesium, we've got 2 of fluorine, we've got 2 of lithium, and just 1 of the carbonate. And after magnesium, we've got 1, carbonate, we've got 1, lithium and fluorine 1. So this doesn't look too difficult to try and balance. If I've got 2 fluorides at the beginning, I'm going to have 2 at the end. So let's put a 2 there. And that's going to give me 2 fluorides and also 2 lithium atoms. And we're balanced. So this is the balanced reaction of this chemical. So enough for having a look at this. I hope that makes sense to you. I will put a link in the description at the bottom so that you can download some of these questions and their answers as well. So let's pull up the slides again, and we finish with this little bit, so I can get rid of that. And let's summarize what we've just had a look at. So on this slide, we've got magnesium plus hydrochloric acid giving me MgCl2 plus hydrogen. You have to remember in all these questions that the total mass of the products is always the same as the mass of the reactants. Things just don't magically appear or disappear. When you're writing the word equations, which they often ask you to do in exam questions, then the reactants always go on the left-hand side of the equation with pluses to separate them, and the products always go on the right-hand side with a plus to separate them, and we join those with an arrow to show they're reacting together. Now, our next part of this topic is all about separating mixtures. So let's have a look at some of the mixtures that you might get and what we might need to try to do to separate them. Let's draw a few out. So let's suppose I've got some sand and I've got some water. Now, sand doesn't particularly well dissolve in water, And so we're just left with sand and water. And if you leave them for a few minutes, they will probably separate happily. But the chemical way that we're going to try and separate these is to use a funnel and a piece of filter paper. And the way of trying to separate these is really quite easy. We have our filter funnel and we fold up a piece of filter paper and put that into the funnel. It usually makes sense to try and draw in some sort of container to collect everything in. So I've done a conical flask here. My art isn't very good. Anyone who knows me knows my art's not very good. And we pour in the mixture of sand and water. The sand gets left behind in the filter paper and the water goes through the conical flask and is collected there. So very easy way of separating some sort of solid plus liquid. What other things might we need to try and separate? Well, our mixture could be slightly more complicated. Let's take a different item this time, and this time we're going to take some salt plus some water. If we put these through the filter, it's not going to make any difference. The salt dissolves in the water and it goes through into the conical flask. So we end up with salty water. So that's not going to be a way of trying to separate the mixtures. So we need a different way. Well, what we can do is we can evaporate the water. And a sensible way of trying to do this would be to take a beaker, take something like an evaporating basin, and if we fill our beaker with some boiling water and we heat it, this salty water will also get hot. The water will evaporate and it will leave for us the layer of salt. So we've got the solid and the liquid, but if we've got something that is dissolved, then we're going to need to separate these, and we'll call this process crystallization. What happens if we've got this process, but we want it to work the opposite way round? I'm not interested in the salt, but I want to collect the water. So I need to try and collect this water. How are we going to go about doing that? Well, our apparatus has to be slightly different. And what I'm going to take is a round bottom flask. There we are, nearly beautifully drawn. And we can connect that to a glass tube. And around this glass tube, we've got another glass tube. And this glass tube is called a condenser. So we have a jacket of water. So we're going to put some cold water in at the bottom, and we're going to get warm water out at the top. So we put our salty water in here, we heat it, and at the other end, let's draw in our flask, and we're going to collect the water. The salt water is heated. The water evaporates, leaving the salt in here. It can't go anywhere else. It goes down this tube where it meets a jacket round this tube of cold water. This causes my evaporated water to condense and to drip out at the other end. And we'll call this process distillation. So quite an easy way of trying to separate these two items. One, crystallization if we want the solid, and distillation if we want to collect the liquid. Well, there are more ways of trying to do this. Let's have a look at some more processes. So if we look at the slide, then another thing we can do to try and separate things, to use either fractional distillation and that of chromatography. Let's have a look at fractional distillation. Fractional distillation consists of trying to separate two liquids. Doesn't actually have to be two. It can be 3, 4, or 5. And to separate this, we're going to use the property that many liquids have, that they evaporate at different temperatures. And our setup's going to be very similar to the distillation, but what I'm going to do is I'm going to put something in called a fractionating column. So here's my fractionating column. It's going to connect to my round bottom flask. And into this fractionating column, I'm going to put a thermometer. So let's seal the end. And we're going to pass this out to a condenser again. These are often called Liebig condensers. I almost leave it to your imagination to wonder why it's called a Liebig condenser. Probably something to do with a Mr. Liebig. And we put in cold water, just exactly the same at the bottom, and we find that warm water comes out at the top. This fractionating column, they look different, lots of different ones. Ones that I have bits of glass rods in there to allow drops to condense. So let's take my liquid. I'm going to heat it. The liquid, there's more than one liquid in there. The liquid that evaporates first will come up to the top, make its way around here, and this sort of tries to separate any of the other liquid that might try to come up first, because it tends to condense on these pieces of glass, whereas the item we're looking for, we collect at a given temperature. So if I've got in here, let's suppose I've got two liquids, we'll go for alcohol and we'll go for water. Alcohol's going to boil at around about 79 degrees centigrade, and water will boil at 100 degrees centigrade. So we heat this up to about 79 centigrade, and we will find that coming down here is going to be mostly alcohol, and I will collect that in my conical flask. So we've got fractional distillation. The last of the items for trying to separate substances is that of chromatography. Most students do this in about year 7, and this consists of taking a fairly large beaker, and we stand in that a piece of paper, which is usually suspended by something at the top. On this piece of paper, we draw a pencil line, usually about 1 to 2 centimeters from the bottom, and we stand this paper in the solvent. And this solvent can be water, but in fact it can be lots of other things. So if we want to have a look and to see whether certain dyes are available in a particular food, I could take my food and put a drop of my sample in here. So this is going to be my sample of food. And I'm going to check it against 2 particular dyes that I want to check are in my food. So dye 1, and here we've got a dot for dye 2. We put this in, we leave for a while, and what happens is the solvent moves up here. We want to get as much separation as we can, and I can't tell you how long to leave something because you're waiting till it nearly gets to the end. My food sample might divide into 1, 2, maybe even 3 bits, and my dyes might separate out. So now I can say this, my food substance has dye 2. It also has dye 1, and here it's got another dye that I didn't test for. We measure this by measuring the distance these have run and the distance how much the solvents run. And we'll look at that in more detail in another lecture. Going back to the slides, we're doing quite well. We're going to have a look at then a little bit about the history of the atom. Where do we get some of this history from? Well, the history of the atom is based on the works of many different people. And the first of these people was a guy called John Dalton. And he came up with really solidified an idea that had been going around for very many years, that atoms are really small things and they're like, well, tiny hard spheres. And this lasted really for many, many years. Dalton just sort of cementing the idea more formally. Around about 1897, a gentleman, Joseph J. Thomson, or just J.J. Thomson, he discovered the electron. And this caused quite a few problems because now they knew that atoms were neutrally charged, and he just discovered a negative part of this atom. So he proposed that the atom is going to look like, he described it as a plum pudding. If we go to the paper, a plum pudding is something that's not familiar to you or I these days, but in fact a plum pudding was quite familiar in those days, and it consisted of a cake mixture with various plums that could be seen. It looks very much like a fruit cake nowadays, and this was our plum pudding model. It doesn't mean much saying plum pudding now, but in those days it was something that was readily understood. So he suggested we had a positive pudding, and inside we had these negative electrons. And so this was what our atom looked like. We go back to the slides. This stayed around for a few years, but it wasn't entirely, I don't know, accepted. And one gentleman, Lord Ernest Rutherford, decided to sort of do an investigation. Now, he'd already won a Nobel Prize for discovering something that came out of an atom, an alpha particle. And he got a couple of his team together, a couple of students. They were probably a bit younger than they are in these photographs. A gentleman by the name of Geiger, and you might have heard of him. He made or invented the Geiger counter. And another gentleman who you won't have heard of, Marsden. And these two students set to work building a piece of equipment. And if we look at this slide, we can see in the top corner, they took a piece of gold foil and they put this gold foil into an evacuated chamber, a vacuum chamber, no air in there. Now, they needed no air in there because they were going to use Lord Ernest Rutherford's alpha particles that he discovered to try and work out about the atom. So they took a piece of very thin gold foil. Now, very, very thin gold foil is only probably 1, 2, 3 atoms thick. So they took this and they fired the alpha particles at them. If the plum pudding model was correct, then the atoms wouldn't let these alpha particles go through. But they did. And this sort of probably cheered a few people up, probably upset even more people. And our plum pudding model was dead because these small little helium nuclei, the alpha particles, went straight through these gold atoms and hit the side. Some of them went straight through. In fact, most of them did. A few of them got bent a little bit. And occasionally, some got turned right around. Let me draw this and show you what's going on. So I've got my piece of gold foil. I've got a very large evacuated chamber. I'll have my source of alpha particles, and the majority just went straight through. A few got deflected either side, and occasionally some came back. Geiger was lazy. He didn't like watching this little screen all the time, so he invented a machine to try and help him do this. And that later came on to be called a Geiger counter. But we've got these particles hitting a screen, and most went through, and about one in every, now I'm going to have to make a sort of a guess at this, something like about 10,000 didn't. And Lord Ernest Rutherford wrote in his journal, it was like firing a 16-inch shell, a gun off a large battleship at a piece of tissue paper, and it bouncing back at you. He was as surprised as everybody else. So he came up with an idea about how an atom might look. He decided that the atom might look like a small nucleus, and going around it in different sort of orbitals, much like planets going around the sun, were these little electrons. And he called this his nuclear model. This didn't last long, because by 1913, Niels Bohr refined this model using other information that he had, and said that, well, what we knew about the atom was these electrons had to be in specific energy levels, and he called those shells. And these shells are what we use now to describe our atom. And all stayed really well now until about 1932, when our model of our atom was complete, when James Chadwick discovered the neutron. So our history of our atom goes from John Dalton with tiny hard spheres to the discovery of the electron by J.J. Thomson in 1897, and he had this plum pudding model. In 1910, then Lord Ernest Rutherford discovered the proton and made this nuclear model of the atom using what's called the Geiger-Marsden experiment. 1913, Niels Bohr put these electrons into shells, and in 1932, James Chadwick discovered the neutron. I'm going to stop there. We've gone through several bits and pieces to start the chemistry, and in our next session we'll have a look at the rest of this and move on to chapter 2. So if you like this, find it helpful, then please subscribe, and I will see you next time. Bye bye.